In this video, I'm going to talk about the equilibrium of rigid bodies under the action of coplanar forces. That's forces acting in two dimensions. The conditions for equilibrium are exactly the same as they were in S1. A system of forces will be in equilibrium if the sum of all the resolved forces in any direction is zero, and if the moment of all the forces about any point is zero. And let's see how we can use this in a practical situation. Here I have a non-uniform rod, AB. Length 4 meters, it's freely hinged to a vertical wall at A. So here's the wall, here's the hinge. The hinge is well oiled, it's freely hinged. It is free to rotate if it wanted to, if it was able to, about that hinge with no resistance. It is held in equilibrium by a string, which makes an angle of 40 degrees with the rod, and the string is attached to the wall vertically above A. The tension in the string is 65 newtons. The mass of the rod is 6 kilograms, so its weight is 6g, but we were told that it was a non-uniform rod. We cannot assume that the center of gravity is in the middle of the rod, so I've put AG equal to x. We're told that the rod makes an angle of 70 degrees with the upwards vertical. Therefore, the weight will make an angle of 70 degrees with the rod. Find the position of the center of mass, so we've got to find x, and the magnitude and direction of the reaction at the hinge. Well, for the reaction at the hinge, I've put in a horizontal component and a vertical component. They're both described by letters, so it doesn't really matter if I put them in the wrong direction, as long as when I use these forces in any equations, I use them according to the arrow on the diagram. If I have put one of these in the wrong direction, then it will come out to be negative. Right. So let's sort out solving this problem. Firstly, I want to take moments. Where is a sensible place to take moments? Well, I think you should all come to here. The point A, if I take moments about A, the moment of H is 0, the moment of V is 0. So if we take moments about A, life is going to be quite easy. Well, let's look at the clockwise moments. The weight will produce a clockwise moment. If I resolve the weight into two directions, 6g sine 70 down there, 6g cos 70 through A. So all I need is 6g sine 70 times x. And the anti-clockwise moments are going to come from the string. Well, the rod is of length 4. Resolving the 65 cos 40 will go through A, no moment. 65 sine 40 times 4. Press the buttons and solve that, and we get that x is equal to 3.02466 with lots of other numbers. We've been using g, so we really ought only to give two significant figures. So there is the position of the center of mass. 3 meters, 3.0 meters from A. We're also asked to find the magnitude and direction of the reaction. If I know both h and v, I can work out the magnitude, root h squared plus v squared, and I can work out the direction. So let's go about working out v and h. First of all, let's resolve vertically. Always tell the person reading it what you're doing. Vertically, I have v. Upwards also. Now I have a slightly more complicated problem. This angle is 70. Another 20 makes 90. So 65 is at 20 degrees to the horizontal. Or you could say I've got 20 here, I've got 20 here, I must have 20 above. So 65 sine 20. V plus 65 sine 20. That's the upwards forces. That must be equal to 6g. Well, that allows us to work out V straight away. 36.56869, and a few more numbers. We want to use V later, so we're not going to reduce the number of significant figures. Another direction which would be sensible is to resolve horizontally. Forces must balance out because we're in equilibrium. H is horizontal, and we get the horizontal component of the 65. 65 horizontally, the angle was 20, 65 cos 20. And pressing the buttons, we discover that is 61.08002 with lots of numbers. So we now have V and H. If we want to add those together, we are looking for the sum of those two being the diagonal of the rectangle. So this length is H, this length is V, there's the angle with the horizontal, and now I've got enough on my diagram to sort out what's going on. The magnitude of the reaction at the hinge is going to be the square root of V squared plus H squared. A little bit of Pythagoras there. And pressing the buttons on that, you get 71.19015 with lots more numbers. And the angle above the horizontal is arctan. And then if we look at the diagram, tan theta is V over H. Theta is therefore arctan V over H. Using all the figures that we have, that gives us 30.909 and lots of other numbers. So the reaction at the hinge is 71 newtons at an angle of 31 degrees above the horizontal. Two significant figures because I've been using G. Notice that I shouldn't say 71 newtons at an angle of 31 degrees with the horizontal. Very definitely, because V and H came out to be positive, the angle theta is above the horizontal. It is not below the horizontal. If you just say with the horizontal, we don't know whether you mean above or below. You can find more on this in your textbook, M2, on pages 1 134 to 139.